To size a transfer switch for an 85 kilowatts, 208/120 volts generator intended for emergency circuits, you must first determine the maximum amperage that the generator can supply at 208 volts. Given that the generator can supply up to 300 amps at an 80% power factor, the minimum transfer switch rating can be calculated using the formula transfer switch rating equals generator full load amperage divided by safety factor. The safety factor is typically 1.25. Thus, the transfer switch rating equals 300 amps divided by 1.25, resulting in a transfer switch rating of 240 amps. Therefore, you should select a transfer switch rated for 240 amps or higher. Next, consider the feeder sizing. The feeder from the generator to the transfer switch must be sized for the maximum amperage that the generator can supply. In this case, the feeder should be rated for 300 amps. Now, let's size the feeder from the transfer switch to the distribution panel. This feeder must be sized for the maximum amperage that the normal power source can supply. Given a normal power source of 208 volts and a power of 85 kilowatts, we first calculate the normal power current using the formula normal power current equals power divided by voltage. This results in a normal power current of 85 kilowatts divided by 208 volts, which equals 408.7 amps. However, the feeder should be oversized by 25% to account for future load growth and voltage drop. Therefore, the feeder from the transfer switch to the distribution panel should be rated using the formula feeder rating equals normal power current multiplied by 1.25. In this case, feeder rating equals 408.7 amps multiplied by 1.25, resulting in a feeder rating of 511 amps. Therefore, you should select a feeder rated for 511 amps or higher. Finally, let's talk about the transformer. To supply normal power to the transfer switch at 208 volts, you will need a transformer. It should have a primary voltage of 480 volts, a secondary voltage of 208 volts, and a power rating of 85 kilowatts. The transformer should be sized for the full load of the generator to avoid overloading. In conclusion, here's the summary. The transfer switch rating should be 240 amps or higher. The generator feeder rating should be 300 amps. The normal power feeder rating should be 511 amps. And the transformer rating should include a primary voltage of 480 volts, a secondary voltage of 208 volts, and a power rating of 85 kilowatts. To further elaborate on feeder sizing, it's essential to consider the type of conductors used and the installation method. The National Electrical Code, or NEC, provides tables that specify the ampacity of conductors based on their size, insulation type, and temperature rating. For instance, NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air, based on ambient air temperature. When selecting conductors for the generator and normal power feeders, ensure that the chosen conductors have an ampacity equal to or greater than the calculated feeder ratings, which are 300 amps for the generator feeder and 511 amps for the normal power feeder. Additionally, dirting factors may need to be applied if multiple current-carrying conductors are installed in the same conduit or raceway, or if the ambient temperature exceeds the conductor's temperature rating. NEC Section 310.15c provides adjustment factors for ambient temperature, and NEC Section 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. Correct application of these dirting factors ensures that the conductors are not overloaded and that the electrical system operates safely. Furthermore, consider the voltage drop in the feeders. Excessive voltage drop can negatively impact the performance of connected equipment and reduce overall system efficiency. The NEC recommends limiting voltage drop to 3% for power, heating, and lighting circuits, and 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals 2 multiplied by the length of the conductor in feet, multiplied by the current in amps, multiplied by the impedance of the conductor in ohms per foot, all divided by 1000. Selecting larger conductors can reduce voltage drop, but it also increases the cost of the installation. Therefore, it's important to strike a balance between conductor size, voltage drop, and cost. Regarding the transformer, it is crucial to select a unit that is specifically designed for the application. The transformer should be a step-down transformer with a primary voltage of 480 volts and a secondary voltage of 208/120 volts. The kilovolt ampere, or kV, rating of the transformer should be equal to or greater than the kilowatt rating of the generator, which is 85 kilowatts. To convert kilowatts to kVA, divide the kilowatt rating by the power factor. Assuming a power factor of 0.8, the kVA rating of the transformer should be 85 kilowatts divided by 0.8, which equals 106.25 kVA. Therefore, select a transformer with a kVA rating of 106.25 kVA or higher. Also, consider the transformer's impedance. The impedance of the transformer affects the available fault current at the secondary terminals. A lower impedance transformer will result in a higher fault current, which may require larger overcurrent protection devices. Transformer impedance is typically expressed as a percentage of the transformer's kVA rating. Consult with the transformer manufacturer to determine the appropriate impedance for your application. Moreover, it is important to install the transformer in a well-ventilated location to prevent overheating. Transformers generate heat during operation, and excessive heat can reduce the transformer's lifespan and efficiency. The NEC provides guidelines for transformer installation and ventilation in Article 450. Ensure that the transformer is installed in accordance with these guidelines. Furthermore, consider the grounding and bonding requirements for the generator, transfer switch, and transformer. Proper grounding and bonding are essential for ensuring electrical safety and preventing electrical shock hazards. The NEC provides detailed requirements for grounding and bonding in Article 250. In general, the generator, transfer switch, and transformer should be grounded to a common grounding electrode system. The grounding electrode system should consist of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, ground plate, or metallic water pipe. Additionally, all metal enclosures and non-current carrying metal parts of the electrical system should be bonded together to create a low impedance path for fault current. Bonding conductors should be sized in accordance with NEC Table 250.122. Also, remember to coordinate the overcurrent protection devices for the generator, transfer switch, and distribution panel. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical equipment and conductors from overloads and short circuits. The overcurrent protection devices should be selected and coordinated to ensure that they will trip or open the circuit in the event of a fault, preventing damage to the equipment and conductors. The NEC provides guidelines for overcurrent protection in Article 240. The size of the overcurrent protection devices should be based on the ampacity of the conductors being protected. The overcurrent protection devices should also have an interrupting rating sufficient to handle the available fault current at the point of installation. Finally, consider the labeling requirements for the generator, transfer switch, and distribution panel. The NEC requires that electrical equipment be properly labeled to provide information about its voltage, current, and other important characteristics. The generator, transfer switch, and distribution panel should be labeled with their voltage, current, and power ratings. The labeling should be clear and legible and should be permanently affixed to the equipment. In summary, sizing a transfer switch and feeders for an 85 kilowatts generator involves several steps, including calculating the generator's full load amperage, determining the required transfer switch rating, selecting appropriate conductors for the generator and normal power feeders, considering voltage drop and directing factors, selecting a suitable transformer, and ensuring proper grounding, bonding, and overcurrent protection. By following these steps and adhering to the requirements of the National Electrical Code, you can ensure a safe and reliable installation. Now let's delve deeper into the selection of the transfer switch. There are two main types of transfer switches: automatic transfer switches, or ATS, and manual transfer switches. An ATS automatically transfers the load from the normal power source to the generator power source in the event of a power outage. A manual transfer switch requires manual operation to transfer the load. The choice between an ATS and a manual transfer switch depends on the specific application and the desired level of automation. For critical applications, such as hospitals and data centers, an ATS is typically preferred to ensure an uninterrupted power supply. For less critical applications, a manual transfer switch may be sufficient. When selecting an ATS, consider the following features. Firstly, the transfer time. The transfer time is the time it takes for the ATS to transfer the load from one power source to another. A shorter transfer time is generally desirable to minimize any interruption in power supply. Secondly, the sensing voltage. The sensing voltage is the voltage at which the ATS detects a power outage. The sensing voltage should be adjustable to accommodate different voltage levels. Thirdly, the engine start signal. The engine start signal is a signal that the ATS sends to the generator to start the engine. The engine start signal should be reliable and compatible with the generator's control system. Fourthly, the bypass isolation feature. The bypass isolation feature allows the ATS to be bypassed for maintenance or testing without interrupting power to the load. This feature is particularly useful in critical applications where downtime must be minimized. Finally, the communications capabilities. Some ATS have communication capabilities that allow them to be monitored and controlled remotely. This feature can be useful for managing and troubleshooting the electrical system. In addition to these features, also consider the ATS listing and certification. The ATS should be listed by a recognized testing laboratory such as Underwriters Laboratories or UL to ensure that it meets safety standards. The ATS should also be certified to meet applicable industry standards such as IEE Standard 446, recommended practice for emergency and standby power systems for industrial and commercial applications. Now let's discuss the installation of the transfer switch. The transfer switch should be installed in a location that is easily accessible for maintenance and testing. The location should also be protected from moisture, dust, and other environmental factors. The transfer switch should be mounted securely to a wall or other suitable support structure. The wiring connections to the transfer switch should be made in accordance with the manufacturer's instructions and the National Electrical Code. All wiring connections should be tight and secure to prevent loose connections and overheating. The transfer switch should be grounded and bonded in accordance with the NEC. The grounding and bonding connections should be made to a common grounding electrode system. Finally, the transfer switch should be tested after installation to ensure that it is functioning properly. The testing should include verifying the transfer time, sensing voltage, engine start signal, and other features of the ATS. The testing should also include verifying the proper operation of the overcurrent protection devices. Now, let's move on to the topic of generator maintenance. Regular maintenance is essential for ensuring that the generator operates reliably when needed. The generator should be inspected and maintained in accordance with the manufacturer's instructions. The maintenance schedule should include the following items. Firstly, oil and filter changes. The engine oil and filter should be changed at regular intervals to ensure proper lubrication and cooling. Secondly, air filter cleaning or replacement. The air filter should be cleaned or replaced at regular intervals to prevent dirt and debris from entering the engine. Thirdly, fuel filter replacement. The fuel filter should be replaced at regular intervals to prevent contaminants from entering the fuel system. Fourthly, spark plug replacement. The spark plug should be replaced at regular intervals to ensure proper ignition. Fifthly, battery inspection and testing. The battery should be inspected and tested regularly to ensure that it is fully charged and capable of starting the engine. Sixthly, coolant level check. The coolant level should be checked regularly to ensure proper engine cooling. Seventhly, hose and belt inspection. The hoses and belts should be inspected regularly for cracks, leaks, and other signs of wear. Eighthly, exhaust system inspection. The exhaust system should be inspected regularly for leaks and corrosion. Ninthly, generator load testing. The generator should be load tested at regular intervals to verify its ability to supply power under a load. 10thly, automatic transfer switch testing. The automatic transfer switch should be tested at regular intervals to verify its ability to transfer the load from the normal power source to the generator power source in the event of a power outage. In addition to these maintenance items, it is also important to keep the generator clean and free of debris. The generator should be stored in a dry, well-ventilated location. The generator should be protected from the elements such as rain, snow, and sun. By following these maintenance practices, you can ensure that your generator operates reliably when needed. Finally, let's touch on safety considerations. Working with electrical equipment can be dangerous, and it is important to take precautions to prevent electrical shock and other hazards. Only qualified personnel should install and maintain electrical equipment. Always disconnect power before working on electrical equipment. Use insulated tools and equipment. Wear appropriate personal protective equipment such as safety glasses, gloves, and insulated shoes. Follow all applicable safety codes and regulations. Never work on electrical equipment when you are tired or distracted. Be aware of your surroundings and potential hazards. If you are not comfortable working on electrical equipment, hire a qualified electrician. By following these safety precautions, you can minimize the risk of electrical shock and other hazards. This detailed explanation covers all the necessary aspects of sizing a transfer switch and feeders for an 85 kilowatts generator, including calculations, component selection, installation, maintenance, and safety considerations.